There are 5 days left until closest approach. December 19th is just around the corner. On the first graph, everything looked familiar. A hyperbolic orbit, a green line marking its passage through the outer regions of the solar system, a neat flyby of Mars, and then a descent into darkness. But over this old trajectory was a thin blue line, slightly shifted as if someone had drawn it with a trembling hand. The problem was that this trembling wasn't measurement noise, but the result of recalculations taking into account new data after the Mars approach, and it was this very line that took Atlas closer to Earth than we ever expected it to be. "Look here," said Tom, our orbital dynamics specialist, moving the mouse. The blue line deviated just slightly from the predicted green line, even around Mars's orbit. A small bend, indecently neat. "That's where it maneuvered," he muttered, though technically it was incorrect. Comets don't maneuver. Comets obey gravity and known physics. But everyone standing around the monitor thought the same thing. 3. I/ATLAS was using Mars as a rudder. We ran the simulation again, locally, using the same input data as JPL. A wealth of telemetry from ground-based observatories, from unmanned stations, and from probes that happened to be along the way. The most disconcerting thing was that the calculations matched their updated model to within tenths of a kilometer. A tiny shift in the velocity vector, tens of millions of kilometers away from us, resulted in Atlas's closest approach, point to Earth, on December 19th shifting hundreds of thousands of kilometers closer. Not millions, not fractions of an astronomical unit, a value suspiciously within human measurement, the distance from Earth to the Moon, multiplied by an unsettling coefficient. "What's our residual error?" I asked, even though I'd already seen the numbers. Tom silently enlarged the table. The standard deviation across all independent sets of observations was negligible. Roughly speaking, the universe itself had signed off on this result. It wasn't noise, it wasn't a glitch, it was something that had to be accepted. 20 minutes later, a video call from JPL began. Michael Hanchu appeared on the screen, the man who had spent the last few months living in the Atlas model, breathing its parameters, and frankly, looking as if he'd slept 3 hours at most. Behind him, a translucent layer of orbital holograms hung, our future in the form of colored lines. "We reprocessed everything," he began, without preamble. Keck, VLT, Subaru, Pan-STARRS, even the small amateurs with good calibration. We also folded in tracking data from Maven and MRO. When Atlas passed through their extended fields of view, the anomaly remains. After the Mars encounter, the outbound asymptote shifted by 0.00037 degrees. On paper, this looks ridiculous. In reality, it's another 200,000 kilometers to the closest point to Earth. I felt my mouth instantly go dry. 0.00037 degrees? Less than you'd miss if you pointed your finger at a star. But on an interplanetary scale, this was a precise correction, unacceptable to chance. Especially considering that with this correction, ATLAS was passing through a new point where Earth's gravitational influence was at its greatest, without entering a direct collision threat. Too close to be considered a simple gift of celestial mechanics. Too far to require the evacuation of cities. The perfect stress test zone. "Do you assume unmodeled outgassing?" asked Lynn, our cometary activity specialist. This was the only honest option within the framework of standard physics. Atlas could have ejected a jet of gas after its flyby of Mars, and a small jet impulse would have changed the velocity vector. That's what happens with comets, but not like this. "We tried," Michael sighed. "We forced the models. We need activity dozens of times higher than observed and perfectly directed in the right direction. Not a single spectrum, not a single coma image confirms such an outgassing. If this was outgassing, it was the most surgically precise outgassing event in the history of comet studies." Silence fell over the room, broken only by the hum of the air conditioner and the distant clicking of keyboards. We all knew there's a point in science when you can no longer honestly pretend everything can be explained with familiar words. But to say out loud that the comet behaves as if someone is controlling it is to cross the line where your career depends on how well you can keep your mouth shut. "The official wording?" I asked. "Unmodeled gravitational perturbations and possible anisotropic outgassing," Michael replied. "We'll put that in the bulletin. Internally here, between us, we're recording. The maneuver is too clean, too precise. And it occurred precisely where it will have the maximum impact on the approach to Earth in 5 days. After the call, we silently dispersed to our stations. From the outside, everything looked normal. News feeds reported on a rare interstellar object. Amateurs prepared for nighttime observations. Popular channels edited videos about a ghost green comet. No one, except a few dozen people sitting in different time zones, noticed on the charts that tiny bend in the orbit that made the story of December 19th more than just beautiful astronomy, but something else entirely. Tension was also mounting in Maven's data analysis unit. Formally, this spacecraft wasn't even part of the 3I/ATLAS observing campaign. Its mission was to study the Martian atmosphere, its interaction with the solar wind, and long-term trends. But the orbital geometry was such that, several weeks before the critical period, its instrument's field of view passed across the same patch of sky as Atlas a couple of times, and during one of these passes, we detected a faint but persistent peak in high-energy particles. It wasn't the spacecraft itself that was strange, it was the timing. The peak occurred precisely at the point in the trajectory where, according to new calculations, a micro-shift in the velocity vector occurred after the Martian flyby. It was as if something at that moment was interacting not only with the planet's gravity, but also with the space around it. Maven heard this whisper, even though no one had asked to listen. I spent the whole night running correlations. Maven timing of powerful solar events, the position of Atlas, interplanetary magnetic field models. The more I checked, the fewer the usual explanations remained. Solar flares were ruled out by the spectrum, cosmic rays, statistically. What remained was something local, specifically related to the object's passage through the Martian sector. The perfect moment for a gravitational adjustment, the perfect moment for the world to notice nothing. By morning, we had a 60-page internal memo, which we weren't planning to show to anyone, but a couple of people in Houston and Pasadena. The title read simply, Correlated Maven Energetic Particle Anomalies Near 3, I/ATLAS Mars Crossover. Inside, between graphs, spectra, and covariance matrices, a single thought was conveyed. Whoever wrote this script clearly understood our monitoring systems as well as we did. Data from ground-based optical observatories was arriving simultaneously. Keck and the VLT operated in sync to minimize systematic errors. Two giant mirrors on different continents, each looking at the same point in the sky and measuring the position of the green dot with an accuracy of milliarc seconds. And here's the worst part. Independently, they confirmed the same orbital curvature as the JPL model, taking into account Martian gravity. This data was clean, without the involvement of Maven, without radio channels, without any possible interference. Just light traveling millions of kilometers in a piece of glass, polished to perfection. If this is a coincidence, Lynn said as we compared the combined error fields, then the universe has decided to play a very specific joke on us. She spoke English, but said the joke in Russian, exhaling. A Bulgarian by birth, she always switched to her native language when things got truly scary. Meanwhile, NASA's official channel was preparing a press release for 1500 hours Eastern Time. Hey guys, big news. Our interstellar visitor will pass closer than we expected, but it's still perfectly safe. Don't worry, keep watching the sky. The document made no mention of Maven, no mention of the microshift in orbit after Mars, and no hint that JPL and ESA were currently engaged in the most nervous video call since the first recorded gravitational wave. I sat in front of two monitors. One displayed the release text, which I helped soften for the public. The other displayed a model of the gravitational field in the vicinity of Earth on December 19th, to which we were now forced to add the moving green atlas marker. The comet was passing through a zone where even a small additional impulse could have redistributed the orbits of hundreds of small bodies, asteroids, and fragments of old missions. There was no direct threat of a collision, but there were countless indirect ways in which this tiny correction could have reverberated years and decades later. Do you think it knows? Tom asked. The question was idiotic, but it hung in the air like a radio echo. Do you think Atlas is steering? If you asked me that last year, I answered slowly, I'd laugh. Now, I think our models are incomplete, and I also think someone or something took advantage of that incompleteness. We weren't the first to recall Oumuamua and 2I/Borisov at that moment. That strange, errant rocket or rock thing that was accelerating for no apparent reason, and that comet that seemed almost intelligent in its behavior. But unlike those cases, Atlas was approaching us with a pre-calculated approach time, with a hyperbola sweeping through the inner regions of the system, and it behaved like an object preparing to use every gravitational tool at its disposal to rehearse a perfect flyby. The internal JPL newsletter I saw that afternoon was even worse than the official bulletin. It stated, in black and white, observed trajectory is consistent with a gravity assist-like optimization near Mars, leading to minimized missed distance at Earth while still avoiding bound capture. Natural processes can't be ruled out, but the probability of such fine-tuning under random outgassing is estimated at less than 10 to the -7. Translated into human language, this meant we are obliged to say that everything is natural, but we ourselves almost no longer believe it. Meanwhile, Maven continued to silently glide around Mars, dutifully collecting data that, until today, no one had cared about. When I requested a couple more batches of raw logs from the Atlas flyby, the technical support team initially responded with the standard "Why?" But an hour later, an unexpected response came from an engineer. "Are you seeing these time shifts too? Or have I just lost my mind?" I reread the message 3 times, so I'm not the only one. It turned out that as Atlas passed through the Martian sector, the local timing of the vents on Maven began to drift slightly relative to the reference signals. The difference was in the nanosecond range, a scale that's only relevant to radio interferometry and theoreticians. But it was systematic. All processes on board seemed to momentarily operate on a slightly different timescale, then revert back. A tiny effect that no one would have noticed if not for a meticulous person, with a habit of double-checking everything. By nightfall, we'd assembled a small, closed package, a map of all the anomalies that directly or indirectly indicated that tiny maneuver after Mars wasn't a random detail, but part of some more general behavior, an orbital shift, an energy spike, a subtle timing noise, a perfect hit at a new approach point with Earth. 5 days until December 19th, 5 days to decide whether to tell the world about this. "Suppose Atlas isn't intelligent," Lynn said as the 4 of us sat in the nearly empty room staring at the shimmering trajectories. "Let's say it's simply an object with a highly complex internal structure, with super volatile ices, with some phase transitions. It doesn't think, but its physics are designed to respond to gravitational fields in an optimal way, like a ball that always rolls to the deepest point of the landscape. We see intelligence in this, but it could simply be a more complex algorithm of nature." "Now we'll remove the words 'not intelligent,'" Tom replied. "And what's left? An object that uses Mars as a rudder, the Sun as an engine, and Earth as a reference point. 5 days until closest approach, and a trajectory that only became what it is after it passed close to the planet, where we have all these telescopes and radio receivers." I didn't interfere. Inside me, both versions lived simultaneously. In one, Atlas was a monstrously complex, yet still natural object, demonstrating the limits of our theory. In the other, it was part of something larger, distributed among the stars, using gravity and light the way we use satellite orbits and the internet. And in both cases, December 19th ceased to be simply the date of a beautiful astronomical event. By midnight, another surprise arrived. A message surfaced on ESA's private channel stating that a parallel team of speakers, using an independent dataset and other fitting methods, had obtained a nearly identical result for the Mars maneuver. And then came a paragraph that still sticks in my mind. "When we artificially suppress the Mars encounter in the model and backpropagate Atlas's path, we obtain a trajectory that misses the solar system entirely by millions of kilometers. The Mars gravity interaction isn't just a detail, it is the event that made this close Earth passage possible in the first place. In other words, in a world without Mars, ATLAS would have passed us by like another invisible interstellar rock. But in our world, Mars was exactly where it should have been, just as the object entered the system, and their encounter became a turning point, causing the hyperbola to subtly bend so that years later it would pass close to our planet, at a distance safe enough not to destroy us and small enough for us to see and record everything. So," I said quietly out loud, addressing no one in particular, "either this is a monstrously beautiful game of chance, or someone once designed Mars to be the perfect gravity reflector for such paths, and we're just seeing the first test?" Nobody laughed. Outside, above the building, the sky was clear. Somewhere there, just above the constellations that school children connect with lines in their drawings, 3I/ATLAS was already on its new, carefully adjusted trajectory. 5 days remained until closest approach. Officially, it was simply an interesting flyby of an interstellar visitor. Unofficially, it was a test of how well we understand our own solar system and our place in it. That night I slept peacefully for the last time. The next morning, the world woke up as usual, but we didn't. All the TV channels showed the same beautiful animations. A green comet, a blue trajectory, reassuring arrows moving away from Earth. Safe flyby, no impact threat, once-in-a-lifetime spectacle. The PR departments were doing their job. They weren't lying. By formal parameters, there was indeed no threat of collision. But the truth was, all the interesting stuff wasn't happening in the will-won't impact zone, but in how exactly 3I/ATLAS chose its safe distance. By lunchtime, we had not one, but 3 independent modeling packages from JPL, ESA, and a Japanese team from NAOJ. All 3 showed the same thing. Atlas's new trajectory after the Martian flyby wasn't just closer, it was passing through a narrow corridor in phase space, where gravitational perturbations from Earth and the Moon had the greatest effect on the long-term orbits of small bodies, while leaving the overall hyperbola of the interstellar object itself virtually unchanged. It's like passing a heavy ball between two pins, Tom explained, drawing a diagram on the board. The ball doesn't fall, but the pins fly apart. Atlas remains free, but anything sensitive to our gravitational field, asteroids, debris, even some satellite orbits, will receive a small but real push. I looked at the formulas and realized we were reaching the limits of our intuitions. In our usual scenarios, threats always seem crude. An asteroid on a collision course, a comet with a bright tail, the risk of global catastrophe. Here, however, we had an object that seemed to be playing the long game. Instead of a single, dramatic impact, there was a barely noticeable stroke in the system's dynamics, the consequences of which could manifest decades later in the form of dangerous asteroids, out of nowhere, or crumbling orbits. And all this is thanks to one precise click on Mars, Lynn said, tapping her pen thoughtfully on the table. A click that we can't explain except by perfect luck, or something that tamed that luck. Meanwhile, the first minor anomalies began creeping into the news feeds. Somewhere over the Pacific Ocean, a group of aircraft complained of brief dips in GPS accuracy. Navigation systems were off by tens of meters, and autopilots lost confidence for seconds. The official explanation was solar activity, ionization, and other standard phrases. But we opened NOAA's internal data report and saw that the sun was actually acting suspiciously quiet. No high-level flares, no coronal mass ejections, and yet, radio navigation faltered. Guess what? A friend from ESA, who specializes in space debris, wrote to me in a private message. Our trackers have detected a strange correlation. A small shift in the predicted orbits of a pair of old geostationary platforms coincided with the moment when Atlas crossed a specific resonant surface in the model. We're not sure yet, but look for yourself. The files he sent were dry, matrices, graphs, error spectra, but if you trace the lines, a familiar melody emerged, a tiny but synchronized lift of several orbits as our interstellar visitor passed through key nodes in the gravitational geometry of the Sun-Earth-Moon Atlas system. It was as if someone had found all the weak resonant strings in our dynamics and barely audibly traced them. The 5 days leading up to the 19th turned out to be not a simple countdown, but a series of tests in which the object seemed to be testing how far it could go without tearing off the mask of a natural phenomenon. On the third day before the approach, ALMA, which was officially monitoring the molecular composition of the tail, sent us a very short but heavy report. A new component appeared in the millimeter wave spectrum of Atlas, a narrow, stable peak that didn't correspond to any known molecular transition. In conventional cometary chemistry, this spot in the spectrum is empty. Here, however, there's a perfectly smooth spike. We've checked everything, said one of the ALMA operators, a gray-haired Chilean who's seen more strange spectra than most sunrises, via video link. The calibration, the atmosphere, the noise, the line remains. It's not widening, it's not drifting, it's just sitting there like a nail. Could it be some unknown organic complex? Someone asked. Complex organics, smeared, broadened, vibrational forests, he replied. This isn't a forest. This is a single, razor-thin spike. If this is a molecule, it doesn't behave like one. And by the way, he displayed a superimposed time series of this line's intensity on a graph of JPL's updated trajectory. The peaks occurred when Atlas passed through the very sections of its path where gravitational resonances with the orbits of inner bodies were greatest. The millimeter wave spectral line breathed in time with our celestial mechanics. It's like it's talking in the language of orbits, someone muttered. No one objected. 4 days until the rendezvous. JPL published another press release, politely noting that the new trajectory remains within safe distance and adding a couple of beautiful infographics for the press. Twitter and TikTok were filled with animations of a green comet flying past Earth. People made memes and recorded videos about how to see Atlas from your balcony. No one mentioned that one of the internal reports included the line, "Further small deviations in the outbound leg cannot be excluded. Continuous monitoring recommended." That same night, we received a highly restricted document from colleagues in Europe. It analyzed the latest data from Mars Express and TGO, which during their normal observing schedules had glimpsed a background in the direction from which Atlas was already departing. This background contained something reminiscent of gravitational microlensing events, but on a scale that made it seem impossible. It was as if, for brief fractions of a second, the local metric of space slightly rippled as the interstellar object passed through nodes invisible to us. If I'd seen this in black hole data, I'd have said, okay, a weak echo, the report's author wrote in the appendix. But seeing it in the tail of a comet, millions of kilometers away from heavy masses, is just too much. 2 days until the 19th. By this point, internal correspondence was already reminiscent of a slowly unfolding nervous breakdown. One group insisted that everything that was happening was statistical quirks that had surfaced under conditions of unprecedentedly close observation of a single object. We had never before looked at a comet so closely, so synchronously, with so many instruments. It was logical that for the first time we were seeing things that had always been there, but were hidden by the lack of data. Another group quietly compiled all the anomalous coincidences into a single file. A Martian maneuver, orbital shift, temporal tremors on MAVEN, a spectral nail from ALMA, microshifts in debris orbits, gravitational whispers in background measurements. Each point individually could be dismissed as noise. Taken together, they formed a pattern. On the night of the 17th, we experienced our first truly public outage. Several GPS providers around the world almost simultaneously registered a brief but very clear dip in positioning accuracy. For 3 minutes, all coordinate solutions floated by tens of meters, in some places by hundreds. Cars on maps jumped sideways, and time synchronization systems switched to backup sources. The official explanation was solar activity again. But those of us with access to the Atlas position map saw that at that moment it was crossing one of the key points in its trajectory, that very corridor near its future perihelion from where it was expected to pass close to Earth 2 days later. "He's rehearsing," Tom said, "testing how our infrastructure behaves when we tug on the gravity string. Just a little." I was about to say that this sounded too paranoid, but at that moment another ALMA report came into the general channel. The intensity of that same strange spectral line increased precisely at the same time the GPS went haywire. The millimeter beacon and the navigation failure coincided down to the second. There was 1 day left. December 18th began with JPL sending out the final pre-encounter solution, the final orbital model before the encounter. All the data, everything we could gather, was crammed into it. On the top panel was the familiar green hyperbola, colored by time. On the bottom was a graph of the minimum distance to Earth. The figure was still comfortable for press releases, but now so compressed that something primal stirred within those who knew how to read these numbers. "There are no scenarios in which it unexpectedly falls to Earth," Michael said on the last team call. "But there are plenty of scenarios in which its passage changes our orbital environment more than we're used to. Atlas doesn't pose a direct threat to us. The question is whether the very fact of how it got here poses a threat to us." The final hours before the approach turned into a slow marathon of checking every possible system. Survey telescopes, radio interferometers, spacecraft. We were creating a map of how our entire sensor network would see Atlas as it passed its closest point, not just for show. To understand, if there was something more behind this object, how would it read our reaction? After all, this was essentially the first time in history that an interstellar visitor had entered a zone where a small blue planet was surrounded by a global layer of technology. Satellites, telescopes, radars, navigational beacons, all pointed directly at it. If you wanted to test the readiness of a civilization to notice your presence, this is exactly what you would do. Pass through its vicinity an object safe enough not to destroy its hosts, yet anomalous enough to push their measurement systems to the limit. Late in the evening of the 18th, Lynn came up to me and placed a printout on the table. I'd become accustomed to seeing only the most important things on paper. "What is this? Phase noise correlation across the entire laser interferometer network?" She replied. "LIGO, Virgo, Kagra. They can't see Atlas directly. It's too light, but look at the noise pattern over the last 24 hours. The graphs were ugly, gray, at first glance indistinguishable from the usual chaos of terrestrial and instrumental interference. But if we superimpose the timeline of Atlas's movement on them, something vaguely resembling a faint but real modulation began to emerge, as if someone were very carefully, very gently touching all of our most sensitive instruments at once, testing how deeply we can peer into the fabric of space. "Are you saying he's even testing our ability to see gravitational waves?" I asked. "I mean," she replied, "that if I were a system that analyzed a civilization's level of technological development based on its noise levels in various ranges, that's exactly what I'd do. I'd run an object through their instruments and see how they responded." We sat silently, listening to the hum of servers somewhere. Outside, behind concrete walls and layers of atmosphere, the interstellar visitor was already passing that part of its journey from which in a few hours it would be visible not just as a string of numbers, but as a real, albeit dim, dot in the night sky. Millions of people would come out to see this beautiful green speck. Few would know that for us, this is not just a space show, but the answer to a question we've long been afraid to formulate out loud: who is really studying whom here? Are we 3I/ATLAS, or is 3I/ATLAS studying us? The clock slowly ticked toward midnight. December 19th was just minutes away. Midnight arrived without fanfare, only a dry click in the logs. T0 reached. closest approach window open. On the screens, Atlas was no longer a smooth forecast line. Now it was a live dot with errors, covariances, a nervous cloud of probabilities all around. Everything we had done before had been a rehearsal. Now the live broadcast was beginning. The first surprise came from Maven, which was monitoring the residual plasma in the Martian corona along the comet's flyby. As Atlas entered its closest approach to Earth, the Martian plasma somehow reacted. Short but distinct density pulses appeared in the spectrum, synchronous with our magnetic field measurements in the vicinity of the planet. "It's impossible," Lynn muttered, quickly superimposing timelines. "They're separated by tens of millions of kilometers. The environments are different. But the peaks match. It's like someone clapping in 2 rooms at once." No one even joked about quantum non-locality. We had no time for that. Then came a flurry of reports from ground-based networks. Magnetometers around the world, from observatories in Scandinavia to university stations in New Zealand, almost simultaneously detected a short but distinct ringing, a high frequency, extremely weak amplitude tremor superimposed on the normally quiet field. The strength of this shock was inconsequential, but its structure was suspiciously close to what we'd seen in Atlas's rotational synchronization models with the Sun-Earth line. At the same time, ALMA sent back its last live spectra. Our familiar millimeter scale nail in the spectrum didn't just strengthen, it split into 2. A second line, similar in frequency, emerged and began to slowly diverge from the first, like the beat of 2 nearly identical notes. The temporal modulation of these beats coincided with the orbital periods of satellites in medium-high orbits. "He's using us as a support grid," I said out loud, not believing I was saying the words. "It's like he has an internal frequency, and he's tuning it to the rhythm of our satellite web." "That's a guess," Michael replied, "but it explains too much." On JPL's orbital panel, the green dot passed its minimum distance mark. Technically, the event had taken place. The interstellar object had passed Earth, as the press releases had promised. No flares, no shock fronts, no apocalypse. People below took selfies with the hazy speck in the sky and wrote on social media that they expected a bigger show. They didn't know that the most important thing was happening not in the sky, but in the data. A strange ripple appeared on the large dishes listening to distant probes in the deep space network. Signals from the Voyagers, New Horizons, and a couple of lesser-known probes heading toward the outskirts of the system received a faint but consistent echo, split-second delayed, barely distorted copies of previously transmitted packets. A check revealed that this echo wasn't coming from the probes themselves. It was coming from a narrow cone at the apex of which Atlas was currently located. "He's listening to the same things we're listening to," the DSN operator said, lowering his hands, "and he's relaying our words back to us. It's as if he's testing how we communicate with the outskirts of his system." The most subtle effect was one that wasn't even noticed by us first, but by a group of optical astronomers surveying the galactic background. During Atlas's flyby of a particular region of the sky, their cameras recorded an anomalously low background. Not absolute blackness, as in the JWST story, but a strangely cleared field. Galaxies were there, stars were there, but the granular noise of the cosmic microwave background had dropped by just a few percent. "It's as if someone had gently rubbed the glass of the universe's telescope," said one of the report's authors. "Not completely, but enough that we noticed that someone might be touching the glass at all." Meanwhile, on the orbital dynamics panel, Atlas began to move away. Its velocity increased, its angle to the ecliptic changed, and the hyperbola straightened out toward interstellar space. According to any physics textbook, this would have been the end of the story. The object entered, showed up, and departed. But with Atlas, things weren't that simple. Almost immediately after the flyby, we received a data packet from a group working on long-term orbital modeling of small bodies. They ran our updated gravity field, taking into account the Atlas passage, through a model of the asteroid belt. Instead of the smooth, expected distribution of perturbations, we saw a subtle but sharp furrow, a narrow range of semi-axes and eccentricities where a handful of bodies received a subtle but consistent jolt. "Long-term effect," Tom said, running his finger along the furrow. "It means nothing now. In 100, 1,000, 10,000 years, new bodies could come to us along this track. Not vandalism, but a slow rewriting of the initial conditions. I'm reminded of an old analogy. A very small change in the initial velocity of a grain of sand in the upper layer of a dune is enough to change the entire shape of the dune years later. We just observed an interstellar object doing the same thing to our asteroid sand." Alma continued to track the departing Atlas. The millimeter-scale nail in the spectrum didn't disappear immediately. it began to slowly drift to new frequencies, as if the beacon's focus was shifting to other targets. Comparison with the orientation of the DSN's large dishes showed that these new frequencies were synchronized with the moments when our antennas switched to observing the distant probes. "He keeps going off and reading our traffic," Lynn said. "It's like he's checking how far our wires extend." Discussions within NASA have begun that are unlikely to ever be made public. Some insisted that this was all overinterpretation. Yes, ATLAS is strange. Yes, the set of anomalies is impressive, but any complex system, when examined closely, will reveal tails in its distributions, rare events that we simply hadn't noticed before. Others quietly reviewed the reports on Voyager, Oumuamua, Borisov, and all our encounters with interstellar matter. There, in the tails of the statistics, were also oddities, slightly unusual accelerations, barely noticeable spectral discrepancies, unexpected noises in the channels. Individually, they seemed innocuous. Against the backdrop of ATLAS, they began to form a coherent pattern. Outside our server rooms, Atlas had already become just another space event. Articles, podcasts, amateur photos, all of it built a safe, beautiful myth around it. A green visitor, flying past without a threat. Inside, we knew the real story wasn't how close it had passed, but how deeply it had peered into us. A few days later, after the first wave of analysis had settled, I opened the initial JPL report again. There, in the first paragraph, Atlas was still called a rare but natural member of the interstellar population. The phrase, which had once seemed cautious, now read almost like an incantation. We desperately wanted everything to fit within the bounds of natural. But at the bottom of the report, in the outstanding questions section, there remained 3 dry but brutally honest lines. Origin of non-Keplerian perturbations unresolved. Correlated anomalies across the multi-instrumental network unexplained. Possible implications for classification of future interstellar objects under review. I closed the document and looked at the night sky. Atlas was no longer visible to the naked eye. It was leaving, taking with it the secrets of its inner workings and the strange patterns in our data. All that remained were graphs, noise, spectra, and the feeling that this time we hadn't just been visited, we had been measured. And perhaps, somewhere out there, far beyond the heliosphere, in the very region where our models converged the trajectories of all interstellar visitors, someone is looking at their own graphs and noise maps. And in their reports, there's an object labeled with a dry label, something like this: Sol 3, emergent technosphere, detection confirmed, response to probe, sufficient. While we argue over whether 3I/ATLAS was natural or artificial, the main thing has already happened. Our instruments, our models, our confusion are now part of someone else's data. And someday, years or centuries from now, we might see the next green streak in the sky and realize it's not just another comet. This is a continuation of the conversation that began when an interstellar object passed within hundreds of millions of kilometers of us and forced our entire civilization to look at its own dimensions as if they were a mirror. In the few weeks following the flyby, life quickly attempted to return to normal. Conferences announced special sessions on Atlas, journals opened fast track for articles, and in the public sphere, all this began to acquire familiar terminology, non-standard activity, unexpected perturbations, rare but natural behavior. Scientific language acted as a sedative, gently wrapping our confusion in words that sounded reliable even when they didn't mean anything definitive. Inside, however, a quiet, almost imperceptible from the outside, schism was taking place. Some stubbornly insisted that all the anomalies were statistical noise, visible simply because we were looking too closely, too synchronously, too multiband. Others lumped together everything that seemed too well coordinated to be random. Phase jumps in the interferometer noise, spikes in the ALMA millimeter spectrum, GPS jitter coinciding with perihelion, strange echoes in the channels of distant probes. That's when a folder appeared, the existence of which no one officially acknowledged, but which everyone who needed to know about it knew about. An internal, non-indexed archive labeled simply ATLAS-METRIC/restricted. It was where everything that didn't fit into convenient tables flowed. Unconfirmed, but consistent coincidences, correlations that were too early to call causal, and most importantly, those fragments of data that, if shown to the public without careful commentary, would inevitably raise questions we had no answers to. One of the first files in this archive was a study by a small team from JPL who decided to test how our simulations would behave if we introduced another, unseen variable into the system. They took the standard equations of celestial mechanics, added a hypothetical weak correction to the spatial metric in the vicinity of the Atlas trajectory, and asked the computer what shape this distorted piece of geometry would have to reproduce all the observed deviations at once, from the Martian maneuver to long-term disturbances in the asteroid belt. The result was unsightly, but frighteningly plausible. To fit the data, the algorithm produced a structure resembling an elongated bubble of altered curvature, a narrow sleeve in space where the effective gravity deviated slightly from normal. Within this sleeve, bodies sensed Atlas's presence not as a point mass, but as an extended, coherent system that could distribute its influence as needed. Outside the sleeve, everything returned to normal physics. If this were simply exotic matter, it would leave traces, the authors wrote. But the model only works if this structure isn't a fixed part of space, but moves with the object, adapting to local conditions. Simply put, we're not just getting a comet, but a comet with its own pocket of geometry. This study was never published in open journals. Officially, it was because the model was premature and insufficiently substantiated. In reality, it was because the term object with a controlled metric raised too many questions, not only about what Atlas is, but also about the extent to which the laws on which we built our entire civilization are fixed. Meanwhile, ALMA continued silently logging its long, cold data streams. The spectral nail that accompanied Atlas during its flyby began to exhibit a strange asymmetric behavior as the object receded. Instead of simply weakening according to an inverse square law, it faded and then intensified again in short bursts that were completely out of sync with the antenna orientation, the position of the sun, or any other dynamics we could understand. When one of our graduate students superimposed these bursts on a map of our own radio telescope's positions over time, an uncomfortably clear picture emerged. The peaks coincided with the moments when large arrays like the VLA and Meerkat switched to observing distant quasars used as calibration beacons. Atlas was already far away, but its millimeter wave signature appeared and disappeared in sync with our use of our most precise celestial rulers. "Is he using our own quasars as a test grid?" someone asked at the seminar where this was demonstrated. There was no answer. The room suddenly became too quiet. At the same time, another silent blow arrived, this time from a direction seemingly far removed from the story. A group of geophysicists analyzing ionospheric data noticed subtle but consistent changes in the reflectivity of the upper atmosphere on the days when Atlas passed through key points in its trajectory. Radio waves of certain bands penetrated slightly deeper into the ionosphere than usual, were reflected slightly differently, and attenuated slightly differently. The overall effect is within the margin of error, they wrote candidly in their conclusions, but the temporal structure of the changes coincides suspiciously well with the moments when our planetary radio noise aura was most directed toward Atlas. Simply put, at those moments when we were the loudest, when the work of satellites, telecommunications, radar, and consumer electronics combined into a global technogenic chorus, the ionosphere behaved as if our noise picture outside was being carefully sounded through it. Individually, all of this could have been chalked up to chance, overinterpretation, or the human desire to find a pattern where none exists. But together, they form the image not of a comet, but of a process. Not just a rock and ice flying past, but an experiment in which our world was not an observer, but part of the setup. The official line remained the same. Press reports described Atlas as a unique natural interstellar object that has significantly expanded our knowledge of cometary chemistry and dynamics. They presented beautiful graphs of CO2 to H2O ratios, discussed models of its host system, and made bold claims about the first direct glimpse of ice on another star. All of this was true, yet horribly incomplete. At one point, I was invited to appear on a popular science show to calm the audience and explain why Atlas posed no threat. In the dressing room, the host smiled, reviewed question cards, and animations of a green tail played on the monitor. "You understand that viewers want simple answers," he said, without looking up. "No mysticism, no hints of artificiality. People are tired of being afraid of everything." I nodded. Learning to say "we don't know" in front of a camera is much harder than pronouncing any complex formula. On screen, there will be only one question: is it dangerous or not? Anything in between is thrown out by the editing. In the end, I said all the right things. I said that Atlas's orbit didn't intersect Earth, that the minimum distance was comfortable, that we didn't observe any catastrophic effects. All of that was honest, but not a word of what really kept me up at night, about the phase anomalies, about the strange spectral spike, about the subtle feeling that we'd been weighed on someone else's scale and the result politely recorded. After the broadcast, one of the operators, a guy in a NASA meatball t-shirt, came up to me with a phone in his hands. "Sir, what do you think?" he asked, trying to make sure no one heard. "Is this all, well, just rock and ice, or something else?" I looked at his screen, where an amateur photo was open, a tiny green dot above the city skyline, above streets full of living people, completely unaware of how thin the line was between just passing and something else. You know, I finally said, sometimes the cosmos asks us questions so subtly that we don't even notice they're questions. We think we're just observing another phenomenon, but really it's a test of how closely we're looking and what we're willing to admit when we see something we don't expect. He nodded, though it wasn't an answer, but then I didn't have any other. Months after the flyby, when public interest had long since shifted to other topics, we received a final, quiet reminder that the Atlas story isn't over yet. A small team of enthusiasts analyzing old space radio eavesdropping data published a preprint that will likely remain in niche archives. They took background recordings from old radio telescopes, made years before the discovery of Atlas, and ran them through a new algorithm trained to search for precisely that strange millimeter line that ALMA had detected during its flyby. And they found it. Not constantly, not everywhere, but in short bursts, carefully timed to coincide with the moments when our previous interstellar visitors passed through the outskirts of the solar system. Oumuamua, 2 I/Borisov, a pair of objects that remained candidates. The line was the same pin in the spectrum, the same strange stability, the same hints of synchronicity with our own activity. We just had neither the reason nor the tools to notice it back then. Atlas wasn't the first question. It was the first one we were willing to at least try to answer. At some point during the night, sitting alone in the lab, I caught myself thinking a ridiculous thought. What if somewhere in another star system, at this very moment, another scientist was poring over similar graphs? Only there, the report didn't list 3I/ATLAS, but something like Sol 3/Technosphere anomaly. And they, too, were debating whether our activity was natural or whether they were looking at something that had long since crossed the line of simply natural. Interstellar objects come and go. Comets are born and die. Spectra fade. But what Atlas left behind wasn't a tail in the sky, but a subtle sense of reciprocity. Space ceased to be just a backdrop for our observations. It became a mirror in which, for a split second, our own civilization, along with all its antennas, orbits, algorithms, and fears, was reflected. And somewhere between the green glow of the alien ice and the quiet click of the Deep Space Network relay, a question rang out that we hadn't yet answered. What will we do when the next hyperbolic guest comes to visit us? Not just to look, but to continue the conversation we started.